Okay, so up to this point, you may have studied algebra in your high school classes or even your college classes, and you may have studied trig as well. But now we're going to turn to the very, very first topic of calculus. So calculus is usually broken into two subjects called differential calculus and integral calculus. But in order to do either of those, we have to first study the concept of a limit. What is a limit? Well, let's imagine we have the function f of x is x squared minus x minus 6 over x minus 3. If you were asked to evaluate f of 3, you might say it doesn't exist because you have a 3 minus 3, which is 0 in the denominator. However, what we could ask is how does this function behave as x gets very close to 3? Not equal to 3, but how does it behave if it's really, really close to 3? So if I want to know what is this like as x approaches 3, we could say we want to look at this and some limit as x approaches 3. So we call it just that, limit as x approaches 3. So we can rewrite this as x plus 2 times x minus 3 over x minus 3. And now you see that we can cancel the x minus 3's. Now, ordinarily you have to be very careful about this because you wouldn't be able to cancel this for x equals 3. But remember, we're only looking at x very close to 3. So it doesn't matter. We won't be divided by 0. So now we just have the behavior as x looks like it's getting closer to 3 of x plus 2. And what does this look like as x gets close to 3? Well, that looks like 5. So we can say that we can look at the behavior of f of x as x approaches 3 by saying, well, we're not going to let x equal 3, but it looks like it's going to approach 5. So let's see what this might look like graphically. So let's look at a graph. Let's just say it looks something like this, where we have a point removed and that point's up here. Let's say that's at A. Well, if this is our function f of x, well, if we say this is at some point, I don't know, 10, and this is at the point 2. We can say we know f of a equals 10, but what does it look like f is going to approach? What's the behavior right here? Well, we can say that as f gets very, very close to a, it's infinitesimally close. In other words, a limiting case of x approaching a, well, that's going to equal 2 because it looks like as x approaches a, f of x is going to approach 2 from both sides. Okay? So another way we can look at this is what does f do as x approaches a from the right side? So if we're looking at the right side, we say the limit as x approaches a, we put a little plus to indicate right. And of course, for this case, that equals 2 because it looks like they're about to approach the same number. If it's from the left side, then we write limit as x approaches a with a little minus sign to indicate left of f of x. And again, that equals 2. So the way we actually define this is if the limit as x approaches a from the right-hand side, if that equals the limit as x approaches a from the left-hand side, then we say this is the limit as x approaches a of f of x. Now you might be saying, when would this never be true? When would a function not approach the same thing from the left and right? Let's look at an example of that. So let's say we have the graph f of x equals 1 over x. Well, that looks something like this. So, if we wanted to look at the limit as x approaches 0 from the right of 1 over x, we can see that as x approaches 0, so we're walking along x as x goes to 0, it keeps blowing up to infinity. But the limit as x goes to 0 from the left, well, we're going towards 0, but from this direction now, we're going to go all the way down to negative infinity. So, we don't get the same thing if we go from the left and right. So, we have that the limit as x goes to 0 from the right is not equal to the limit as x goes to 0 from the left. So, we say the limit does not exist. So, for a limit to exist, its limits have to be the same on the left and right. What if we change this just a little bit? What if we said instead of 1 over x, we have 1 over x squared? Well, now our graph looks like, still looks kind of like that, but now we have something that looks like this. So, the limit as x approaches 0 from the right of 1 over x squared is still going to be infinity. But now we also have the limit as x goes to 0 from the left. Well, now we're approaching 0 from the left, but look, we also get infinity. So, the limit from the left equals the limit from the right, therefore we conclude the limit exists. So we can write the limit as x goes to 0. We don't have to put a plus or minus because this is just in general for both sides. Of 1 over x squared is infinity. Let's look at another typical example that might come up of them not equaling each other. So let's say we had some sort of function that looked like this. Now, if you remember back from your high school or early college years, whenever we have a closed dot, that means you're including that point. Whenever you have an open circle, that means you're not including it. So, this is included in the function, and this is not. So, if this is our function f of x, okay. So, we call this point, let's say 1, and this point 2, just to have some numbers. Well, we can see that the limit as x goes to a from the right is going to be, well, we're approaching a but never touching it. So it's still approaching 1. And from the left, well, if we look at it from the left, it's approaching the value of 2. So we can say that the limit does not exist because they're different on both sides. Okay, so let's talk about what it means if the limit as x goes to a exists. So let's say the limit from the left equals the limit from the right. But let's say that also equals f of a. So what would this mean? So if we just take an ordinary function, could be anything, let's say it's f of x equals x cubed. Nice, well-behaved function, no asymptotes or anything like that. Let's say we wanted to look at what happens when x approaches 3. So limit as x approaches 3 of f of x. Well, as f of x approaches 3, it approaches the same value from either side. Okay, so the limit exists, and it approaches the f of x value, f of 3, which is 3 cubed. So, we can say that the limit equals the function at that point. If this is true, if this statement is true, then we say that f of x is continuous. So, a simple non-rigorous definition of continuous is, can you draw the graph without picking up your pencil? Well, I can draw this without picking up my pencil. However, I can't draw something like that without picking up my pencil because there's a discontinuity right here. It's not continuous at that point. So we say that that graph is not continuous. Just the same way that when we had our graph that looked like this, even though the limit existed at A, the limit of f of x is not equal to f of a, if this is our f of x. Because the limit approached this value, but the actual value is up here. So this is the discontinuous function at this point. Now everywhere else is continuous. It's continuous here, it's continuous there. But at this point, that's a discontinuity, so we call the function discontinuous. So let's look at an example of another one. So let's say we had the limit as x approaches 7 of x squared plus 8x plus 7 over x minus 7. No, let's not do that. Okay, so in general, what you want to do for polynomials is just as we did before with the x squared minus x minus 6 over x minus 3, you want to look for things you can cancel, okay? There are trickier limits, such as the limit as x approaches 0 from the right of the natural log of x. For limits like these, you kind of just have to figure out what they are by looking at the graph or plugging in numbers. So for stuff like this, you would have to know that the graph looked roughly like that, so you would get negative infinity. So a lot of these you can solve graphically, and the polynomials you can solve by factoring out. Okay, so that's the concept of the limit, continuity.